Hi, in this second tutorial, we are going to explore our first real-world data set on dengue fever cases. So we're first going to learn about dengue fever and the impact that climate change will have on dengue fever cases. Then we're going to see how we can use linear regression to try to predict dengue fever cases. Then we're going to learn about an alternative machine learning model based on decision trees that can also try to predict dengue fever cases. And then finally, we're going to learn about the concept of feature importance and what it can tell us about our models. So let's first talk about the health impacts of climate change. There are many health impacts of climate change that is beyond the scope of this particular tutorial, but we are going to focus on dengue fever. So dengue fever is a viral infection. It can cause fever, headache, muscle pain, nausea, and rash. The severity can range. Some people don't notice it at all, and for some people, in rare circumstances, it can be fatal. So according to the World Health Organization, between 100 and 400 million infections occur each year. Dengue fever spreads through the bite of an infected mosquito. It's most common in regions where mosquitoes are common, so tropical and subtropical regions. And there isn't really a cure directly for dengue fever, so it's mainly prevented by controlling and avoiding mosquito populations. So that's how it's currently controlled, but as you can expect, with climate change, it will become more of an issue. So specifically, climate change is predicted to affect dengue fever cases because temperatures impact mosquito development and survival. Warmer temperatures are more supportive of mosquitoes. Mosquitoes are also more prevalent in periods of high rainfall and humidity. So the idea that there will be more extreme rainfalls at certain times, higher humidity, more precipitation, that's also going to support the development and survival of mosquitoes. So there are studies that have looked into the impact of climate change on dengue fever and other mosquito-borne viruses. And this suggests that with 2 degrees of warming above pre-industrial averages, the region where dengue fever is present will expand, and the duration of time in a given year that it's a problem will also increase. So there will just be more regions in the world where mosquitoes that carry dengue fever are present, and they'll be active for a longer portion of the year. So that's why understanding the impacts of climate change, understanding how climate change relates to health, will be important for preventing things like dengue fever. So the data set that we're working with about dengue fever comes from this website, Driven Data. And this particular data set was collected by the US and Peruvian governments, along with some US universities and the US's NOAA, National Oceanic and Atmospheric Administration. So the data set that we have is a combination of climate variables and measures of dengue fever in 2 different cities. So what we want to do with this data set is see if we can predict the number of cases of dengue fever based on the environmental and climate data that we have for those locations for those weeks. So we have for each week a set of climate variables and the number of dengue fever cases that were documented in that region. So the specifics of this data, the features that we have, the data was taken from 2 different locations, 2 cities, San Juan and Iquitos. And we know the week of year that the data was collected and the start date of that week. We know things like the vegetation. So the NDVI, which you encountered in your remote sensing tutorials, the difference in vegetation index, that is a measure of vegetation and growth, and we have that for different locations around each of these cities. We also have measures of the weather. We have maximum, minimum, and average temperatures, total precipitation, dew point, humidity. And for some of these variables, you actually have multiple measures because they're sampled from different sources and also sometimes with different spatial resolution. So you'll see multiple different measures of things like temperature in this data set. So those are all the features that we have that should tell us something about the state of the environment at a given time. And our hope is to be able to relate that understanding of the environment to the number of weekly dengue fever cases that were measured in each of these cities. So the first thing that you're going to do with this data set is to just explore it. Before you try to train any model, you're just going to kind of plot some of the variables, try to understand the features of the data, look for any missing data, that kind of thing. It's very important when you get a data set to do a little exploration to understand the properties of the data and how high quality the data set is. Sometimes in the real world, you're working with data sets where for whatever reason, there's many missing data points. Maybe they weren't able to take a certain measurement every single week. And so sometimes there's missing data points and you have to decide what you're going to do with that in order to continue analyzing your data. So you always want to just take a look at it, get a sense of what the data is like before you start building any kind of model. Then you're going to try to apply linear regression to this model. So as you'll recall from the previous tutorial, in linear regression, we're trying to predict the target variable y based on regressors x. And so in this case, y is the weekly number of dengue fever cases, and x is all of these weather and environmental variables that we have associated with those weekly cases. So it looks something like this. We want to predict the weekly case numbers based on things like temperature, precipitation, and all of those other features in this data set. So that's the relationship that you're going to try to learn using linear regression. So you're going to combine what you learned in the last tutorial working with the synthetic data, and then you'll have an understanding of this dengue fever data set. By exploring the data set, you combine those things together and you train this linear regression model to try to predict weekly case numbers. Now, something to think about when you're working with this is, this is a real world data set. People want to be able to predict dengue fever cases for things like preparing doctors, also for prevention. If you understand what causes an uptick in dengue fever cases, then you can try to help stop that uptick. So you need to be thinking about real world evaluation. We talked about things like R-squared and how you evaluate a regression model. That's very important to understand the mathematical side of evaluation. But then you should also think about, in the real world, what would this mean? So for example, how do people try to predict dengue fever cases right now? If they're not using any machine learning model, what kind of methods are they using? Do they have simple heuristics that they use to anticipate an uptick in dengue fever cases? And does this model actually perform better than that? Or are the current practices kind of sufficient and the machine learning model isn't adding anything? Also, you have to consider what types of differences matter in practice. If you could build a machine learning model that can predict dengue fever cases, only slightly better than what's currently available, does that matter? Is catching one extra dengue fever case, like predicting one extra dengue fever case, how is that going to matter in practice? Sometimes small differences in model accuracy can make a huge difference in the real world, and sometimes they don't make that much of a difference. So it's just something to think about in the context of what the model would be used for in the real world and what kind of performance would actually be helpful for people on the ground trying to use this information. And then there will also be some bonus sections in this tutorial that kind of go beyond the simplest, cleanest version of linear regression. So you'll learn how to handle, if you do the bonus sections, things like non-numeric features. So for example, we saw in the feature list here that we know which city the data came from. That's not a numeric value. There are ways to put that into the model, though, if you wanted to include which city as part of the information you're providing the model for predicting cases. Also, what we're working with here is called count data, because we're dealing with a number of cases. So these are integer values, and so those actually have some special mathematical properties, which means that basic linear regression isn't always the best approach. And so you can see an example of how to kind of zhuzh the regression up a little bit so that it can interact with count data. So those are bonus sections that are optional. The next thing that you'll do is try to work with a new method entirely and compare it to the linear regression model. And so that new method is based on decision trees. We're not going to get into the full details of how decision trees work here. I'm just going to go over the concept. But as you saw with linear and logistic regression, the way scikit-learn is built, it's really easy to try new models because the interface is the same for all different models that they have. And so you'll be able to use these models, even though we're not going to go into detail of the mathematics of how these models are trained. So decision trees can be used actually for classification or regression. And they solve problems through a series of binary decisions. That's why they're called decisions. And when you do this series of binary decisions, you get this structure that looks like a tree with all these branches. And so the way it works is that you would put in some data, a data point, and the model would go through these series of binary decisions. So at first it might say, if we're trying to predict dengue fever cases, it might say, okay, what is the temperature? Is it above some threshold? And if it is above that threshold, you go down this branch of the tree. If it's not, you go down this other branch. And maybe the next decision point after if you're above that temperature threshold is, what is the humidity? And if you're above that threshold, you go one way. And if you're below that threshold, you go another way. And the model does this. It keeps going and going and going until it gets to some endpoint that's associated with different numbers of dengue fever cases. So if you have high temperature and high precipitation, you might go down this whole tree and it might say, oh, it will be, however many dengue fever cases this week, several hundreds perhaps. And you might go down a different route with a different data point that will result in only a small number of dengue fever cases. But so the point is that the model is splitting each input feature, thresholding it, and kind of taking the data point along a different path to get to a different output. That's how these decision trees work. And so the training process centers on finding these decision points. So should the first decision point be temperature? Should it be other features of the weather? What should the first decision point should be? And what should that threshold actually be, that temperature threshold, if you're working with a continuous variable? So those are the kinds of things that the model has to learn. Again, we're not getting into the details of that here, but that is how the model is learning to solve the problem based on seeing the training data. And so the specific model that you'll be working with in scikit-learn is actually called a random forest model. This is simply a collection of decision trees. So it's called a forest because it's a bunch of trees. But the idea behind using more than one decision tree is this idea in machine learning called bagging or ensemble methods. It's just the sense that kind of if you have a crowd, that's going to be more intelligent than any individual, you know. So you train these decision trees. You could just use a single decision tree to get to your prediction. But if you train a bunch of different decision trees that have different properties or are trained on different subsets of the data, then they all specialize in their own part of the problem, and then you take their average as your output, and then you should get an even more accurate output from the model. So it's just the idea that if you have many models where they each kind of make their own errors, when you average their outputs together, you get fewer errors. That's the idea behind these bagging or ensemble methods. And you can do it with all different types of models, but when you do it with decision trees, it's called random forests. So that's the method that you're going to use. It's going to use a bunch of different decision trees that are all trained on this data set in order to get the kind of smartest possible model. One good thing about decision trees and random forests are that they can fit relationships that are not purely linear. So as we saw with linear regression, you're trying to fit a line to the data, and that will work if the relationship between the regressors and the target value is roughly linear, if it follows a line. But you can imagine many different relationships between the X and Y values in a data set, and most data sets in the real world don't have that kind of simple linear relationship. And so things like decision trees and other more advanced machine learning models, they can fit these non-linear relationships. And that's something that's very powerful and useful about these different types of methods. Okay, and then the final thing that you're going to look at is feature importance. And so feature importance is something, a kind of methodology you can apply once you've built a model. And the idea of feature importance is that it gives you an indication of which input variables the model is using for its prediction. So you're going to provide the model with all of these different measures of temperature and precipitation and humidity and all of these things. And the question is, which of those things does the model actually care about? Which did it learn are actually important for making a good prediction? And in scikit-learn, there are a variety of different feature importance methods that are available to try. But no matter which method you use, it is important to take care when you're interpreting these feature importance values. So what these feature importance values tell you is something about how the model works. It's telling you something about how the model is taking in inputs and turning those into the outputs of the model. It's not necessarily telling you how the world works. So for example, you might see in the feature importance methods on the dengue fever data set that maybe precipitation is, that value is a really important thing that the model uses to predict dengue fever cases. Maybe that's something that's important to the model. That doesn't necessarily mean that knowing precipitation in the real world is going to tell you about dengue fever cases. It's the relationship that the model learned, but sometimes the model can learn those relationships for the wrong reasons. So that's just some caution to have. It can be useful to understand how your model is working. You can use these feature importance methods. And the goal is eventually to be able to say something about how the real world works if your model is capturing the relationships that exist in the real world, but you have to be careful in interpreting those. Okay, so to just summarize what you'll be doing, you're going to explore the dengue fever data set, then you're going to train a linear regression model to predict cases, and then you're going to compare that to a random forest model for predicting cases. And then you're going to look into some of these feature importance methods to see if you can figure out which inputs from the data the model is using to predict the cases that it's predicting.